Okay, so let's try an optimization problem here. If 1,200 square centimeters of material is available to make a box with a square base and an open top, find the largest possible volume of the box. Okay, so we're being asked to, largest possible volume, to maximize volume. We'll call it V. So this, we're doing a box here, so we've done a similar problem, but it was a little bit different. We were trying to minimize how much material we use. Now we have a certain amount of material here, and we want to maximize the volume we get. So it is going to have a square base, so I'm going to call that XX, and then the other dimension I'll call Y. Okay, and it is open at the top, so we will not be including that. Alright, so the volume that we're trying to maximize would be x times y, or x squared y. Okay, so then we've been told about the material, but that's coming from the surface area of the box. So the surface area, which would be the base, x squared, plus the four sides that have area xy. And that, we've been told, is fixed at 1,200. That will allow us, so what I think I should do here is try and solve for y here, because we get 4xy equals 1,200 minus x squared. So y is going to be 300 over x minus x over 4 when I divide both sides by 4xy. Okay, by 4x, sorry. Alright, so that will allow me now to write my volume only in x as x squared times 300 over x minus x over 4, or in other words, as 300x minus x cubed over 4. All right. So where am I? I'm at this point where basically I'm trying to maximize V of x equals 300x minus x cubed over 4 on some interval. So if I'm going to have a box, and I can't have x be 0, so just bigger than 0, so open 0, and then how big can x get? Well, realize that we need y to keep from getting 0. So if I see when that happens, 300 over x minus x over 4 equals 0, this comes out to be this is going to give us x squared is 1,200, x is plus or minus square root of 1,200. We can forget about the minus right now. We're only interested in positive lengths. So x is 400 times 3 is 1,200, so take out 20 as the square root of 400, radical 3. So x can only go up to and not include 20 radical 3, because that's where y would then become 0, and that's not going to work. Okay. So I'll need the derivative, 300 minus 3/4 x squared. Okay. I want to know when this derivative is 0, or when this derivative is undefined, and the original problem, the original function, is defined. Okay, but there's no issues with the derivative that way. If I do 300 equals 3 over 4x squared, that would give me that x squared equals 400. X is plus or minus 20, but obviously we're only concerned with positives here, so x is 20. So if we look at going from between 0 and 20 radical 3 and go 20, this is v prime, let's see what's happening. So if, here's the derivative, if I plug in 1, I get 300 minus a small number, so that's positive. If I plug in something close to 20 radical 3, so that's a square root of 1200. If I put approximately that in, this is going to be like 1200. This is going to be very big, the 3/4 x squared, so 300 minus that is going to be negative. So we have increasing then decreasing. We have a relative max here, which, because it's always increasing before and decreasing after, becomes an absolute. Oops, an absolute max. All right, and so what are we supposed to find here? Find the largest possible volume of the box. All right, so this means that we would want x of 20. Y then becomes 300 over x minus, what was it? X over 4. So that's 300 over 20 minus 20 over 4. That's 15 minus 5, so that's 10. So y is 10, x is 20. Oops, 20. Y is 10. That didn't really answer it. We want the maximum volume that occurs there. So the volume was x squared y, 20 squared times 10, and that would be 4,000 centimeters cubed in this case. So that would be the optimized volume.